energy transfer in chemical reactions. A chemical reaction is the breaking apart of an old bond or a new one coming together. And the reactants are reacting to become the product. And the reactants have the same mass as the product. That is the law of conservation of mass. So the product has the same mass as the reactants had to become the product. All the chemicals reactions in the human body are called metabolism. There's potential and kinetic energy. Potential energy is the energy which is where it could become something, like the food can be when it becomes something, and energy cannot be destroyed or created. So that is the law of conservation of energy, but it can be converted. It can become potential energy in the form of food, can be converted into kinetic energy, to walk, to talk, whatever. And there are exergatic reactions and exergatic, whereas at the end less energy in the products, because there was a lot of energy released when new bonds were formed and only a little absorbed when they were broken apart. And endoganic reactions, there is a lot of energy in the products because there is only a little released when they are put together and a lot absorbed when they're broken apart. And now we need activation energy to do it all, but it is the case that we're having kinetic energy, molecules and ions and so on, they're moving around, and when they collide together, then we can have that valence electrons, they are bounding or breaking and doing things, that makes them the chemical reactions, but we need activation energy to move like that. And it can be made easier that these reactions are happening more likely by having just more of these molecules, or a higher temperature when they're also moving faster. But there's now the idea of catalysts. In the human body, these are enzymes, and these enzymes, they are lowering the activation energy necessary to do this bumping together, changing the electrons, the valence electrons to do a chemical reaction, and giving or getting energy, whatever. And also, do they orientate them rightly? They also are more likely or better, or only when it is possible, if they come together in the right, hit each other at the right spot. And that is according to Gerhard Toga and Selakowski's Principles for Anatomy and Biology book on several pages, for example 34, 35 and 36. But this is no medical advice. Hi Gregson, I'm trying to learn biochemistry. Today, activation, energy and catalysts, and after we've done that, we're gonna do arm strength training. And if you participate in the arm strength training, then it's at your own risk. Activation energy. Because particles of matter, such as atoms, ions and molecules, have kinetic energy, they are continuously moving and colliding with one another. So atoms, ions and molecules just have kinetic energy and they are colliding with one another. A sufficiently forceful collision can disrupt the movement of valence electrons, causing an existing chemical bond to break or a new one to form. So these atoms can bump together, and the electrons at the outside of it can now get lost, break apart, they can disrupt the movement of valence electrons, and it can now happen that they stick together now, or they will also break apart a chemical bond. The collision energy needed to break chemical bonds in the reactants is called the activation energy. Activation energy is the energy needed to bring them on collision courses. And during the collision course, it can happen that they're breaking apart and are now again two molecules or whatever, two chemical things, or to stick together. This is the initial energy investment that is needed to start a reaction. The reactants must absorb enough energy from the surroundings so that their chemical bonds become unstable. And the valence electrons can interact to form new combinations. Some way do they absorb energy, or they're moving around, or something like that, they're having kinetic energy, they're bumping together, then they bump together, it can happen that they stick together or break apart. Then, as new bonds form, energy is released to the surroundings. Two factors influence the chance that a collision will occur and cause a chemical reaction. Now we're saying when a new bond is formed, there's energy released. I still don't understand why and how, but there's energy released. and that two factors with influence on when a collision will occur and having then a chemical reaction. The first one is concentration. The most particles of matter present in a confined space, the greater the chance that it will collide. The concentration of particles increases when more are added to a given space, or when the pressure on the space increases, which forces the particles closer together so that they collide more often. So the more particles are in, the more likely they collide. And then there are more particles of it. But once it is more likely, if there are more red cars, it is more likely that a car which has collided was red. Basically, that's what you're saying. And also, if the area gets smaller, so if there are not longer 4 lanes, but just 1 lane for both directions, and there are only red cars driving. Number 2, temperature. As temperature rises, particles of matter move more rapidly. So if the temperature is higher, these particles are moving faster. The result is that up to a point, the higher the temperature of matter, the more forceful particles will collide, and the greater the chance that the collision will produce a reaction. We did that right now in helioscience. There's talking about that if the inside of a star or a sun are at over 10 million degrees, they are moving so fast that they're overcoming their electrostatic repulsion and sticking together. I think what they mean is 2 hydrogen atoms inside of a sun or a star don't want to stick together. They're having electrostatic repulsion. Why? I don't know why. Maybe because they have just one electron, whatever. They don't want to come together. They are like magnets which are repelling each other. Whatever. But if they snow very hot, over 10 million degrees, they're moving very fast. And when they're moving so fast, suddenly that moving is stronger than their imaginary spring can stop them from bumping into each other, forming helium. And I think what is what we're talking about. Now with helium then makes an outward force as radiation, whatever. That is basically how the sun works. And there's saying here now, the result is that up to a point, the higher the temperature of matter, the more forcefully particles will collide and the greater the chance that the collision will produce a reaction. I think I understood it so far. Catalysts. As we have seen, chemical reactions occur when chemical bonds break or form other atoms. So a chemical reaction is forming a new bond or breaking one apart. Atoms, ions, molecules collide with one another and so on. Molecules colliding with one another is also one. As we have seen, chemical reactions occur when chemical bonds break or form other atoms, ions, or molecules collide with one another. Normal temperature, I don't think we should take them too literally here. Normal temperature and pressure within the body are too low for most chemical reactions to occur rapidly enough to maintain life. I a little bit forgot what idea I had. But basically we still have this interesting. Normal temperature and pressure within the human body are too low for most chemical reactions to occur rapidly enough to maintain life. Raising the temperature and the number of reacting particles of matter in the body could increase the frequency of collisions and thus increase the ratio of chemical reactions. But doing so could also damage or kill the body's cells. That is how it works. Substances called catalysts solve this problem. Catalysts are chemical compounds that speed up chemical reactions by lowering the activation energy needed for a reaction to occur. A catalyst does not alter the difference in potential energy between the reactants and the products, it only lowers the amount of energy needed to get the reaction started. So there's less energy needed to bring them to work. Like in our traffic example, the cars don't need so much fuel to run. We don't need 10 diesel liter per 100 kilometers, we need just 5 or 3. For chemical reactions to occur, some particles of matter, especially large molecules, must not only collide with sufficient force, but they must hit one another at precise spots. A catalyst works by helping to orient the colliding particles of matter so that they touch at the spots that make the reaction happen. I don't know what exactly now, but I think we're turning them around. This is my explanation, whatever we have to talk about. So we're all like, wait a minute, and the valence electron is here and here and here and here. And now if they hit together, they're bumping out with the other part together. I don't know how long I want to use my traffic example because it could be, this is a little bit morbid to use it, but basically if we're having the valence electron here and the bump together, it doesn't happen so much. So we're having to have a valence electron at the right side, and if they're coming now in the right position or something against each other. And the catalyst is somehow doing that. Maybe, I have an idea, the catalyst docks onto that atom which should do it, and goes then onto that one side, and basically turns it around, like hanging a heavy weight onto something, and that makes it hang down. I don't know how it is now because I describe. I don't have an example. I don't know what's something with pedals. Now I forgot an example. I had a little example, but I forgot it again. Now we're talking on. These things which fall over and go up again. So we're having the massive part of it. There is a Stanley Law and Oliver Hardy movie it is our relators from 1936. In one scene, I'm going to talk again about something morbid. They were getting cement onto their feet because they're having a gangster area and they should be killed. They don't be killed, they survive. But and then because we're having that at their feet, they can fall over and they're going back because the mass of them is just at the feet. They can fall over and go back again. And they also play things, whatever they have also. But so many mass in the round place at the feet or at the bottom of these toy things. And when they're falling over, but they're just standing up again. They're impossible to lie down. Now my idea is that these catalysts, medicamentation, whatever, coming onto these particles and then they're docking somewhere and then making them. It doesn't really work because they're in a massless room or whatever. But basically they're taking it away, so basically went all in that direction or whatever. And if they bump now together, they always do it with one valence electron. A catalyst works by I have no idea if it's true. A catalyst works by helping to orient the colliding particles of matter so that they touch at the spots that make the reaction happen. Although the action of a catalyst helps to speed up a chemical reaction, the catalyst itself is unchanged at the end of the reaction. Thus a single catalyst molecule can be used repeatedly to enable many chemical reactions to occur. Because the catalyst itself is not reacting? I think that's right. Thus, a single catalyst molecule can be used repeatedly to enable many chemical reactions to occur. The most important catalysts in the body are enzymes, which we will discuss later in this chapter. So, enzymes. Enzymes coming there. And we're docking on and exposing that one valence electron. And if they now hit together, they're hitting together at the right spot and the reaction can happen. And also the potential energy is lower. Maybe because we know, how can the potential energy get lower? Can we use our example? I'm not able to form it right now. I have no idea if it's true. But we're supposed to be written about catalysts. Now, we read now what was here written about catalysts and activation energy. I think we understood at least something. I don't know if we understood what they explained to us, but we understood something. If you were here for biochemistry, you can go directly to the next one, biochemistry. We will continue reading about it, and then we find out if we understood it, right? If you stay here and participate in the Armstrength, 20 minutes with your own risk. Go to stable stance and cover the arms to the side and reach with the fingertips as fast as possible. And again down. And to the side. And down. And now reach in front. And now, if this exercise causes pain or discomfort, then down to it. Fists and go in front and circle the fists. The flail exercise. And other direction. Now, long arms, but not completely locked, outlook. Little bend in the elbows and press the fingertips together. The star exercise. Now we're having rules. If there's pain, stop immediately. Have a little bend in the elbows, and if there's pain at the elbows, at the wrists, at the fingers, or in particular and the finger joints will stop immediately. And you also don't have to do it with full effort. It's actually better not to do it full effort, because your arm muscles are probably stronger than your finger joints can hold. And next exercise, now with longer fingers. Again, little bend in the elbows. And if there's pain at the elbows, wrists, fingers, or joints, stop immediately. And next exercise. Press with the fingers into the finars, the finar and hypophinar of the hand. If this causes damage at your skin from the nails or damage at the nails, then don't do it. So press and up again. And again, if there's pain or discomfort at your wrists or fingers or something, don't do it. Stop. Press again. And over. And on the other side. Press. And over. Other side. Press. Again. Press. Up. You don't have complicated times. Up. And the other way around. And again. Press. Up. And press. Up. And press. That's another one. I forgot. So arm out. Press. Go in. Press. And the next one, press with the hands together, out to the side, high up, not completely up. Keep a little bend in the elbows. You don't have to do it the full force over to the side. Down, middle, and in the other direction. Over, up, over, down, middle, and press again. Middle, up, over, down. Change over, down. Arms to the side circle in front and backwards. And one arm in. Go on. And that was the Armstrength training. Thank you very much and